Hi everyone. I just finished my second year of graduate studies at the University of Delaware, and like she said, I'm going to be talking about the effects of distance photoevaporation on planet migration. So first I'll just talk about the motivation for studying planet migration, and I'm going to try to hopefully teach people who don't know much about planet migration a little bit, give them a better idea of how it works, and then go into photoevaporation and how the two go together. So this is the sort of motivation behind studying, or this project in planet migration is trying to figure out why there's so few Jupiter-mass planets between about 0.1 and 1 AU. I guess people in the past who have done similar projects have said why there are so many Jupiter-mass planets between 1 and a few AU. You can kind of phrase it however you want, but I don't want to argue about detection biases or anything like that. So why do planets stop around 1 or 2 AU before they get to this distance? So this is the planet migration slide where hopefully I can teach you everything you need to know about planet migration. And thanks to David Sang for making this beautiful picture. So we'll start, let's see if we can get it. So we'll start looking at the planet here. And there are outer resonances and inner resonances. These are just integer period ratios, 1 to 2, 2 to 3, etc. Periods with the planet. So the disk material at those locations gets excited by the planet, and density waves travel away from the planet, and the ones outside the planet's orbit will torque the planet inward, and the ones inside the planet's orbit will torque the planet outward. So I call these green resonances green for go resonances, they make the planet go, and blue resonances are blue for brakes because they make the planet stop, and they're not blue for backwards because green tends to win. So either you're going forward, these are the per resonance torques here, either you're going forward or you're going forward slower, depending on the density distribution around these resonances. And I also just want to note that, first of all, the resonance strength increases as you get closer to the planet, but then it decreases as the resonances start to overlap with each other. But the torque density still diverges for a point particle, which planets aren't. But just note that it keeps increasing as you go closer to the planet. So without Newton's third law, this would mean that actually basically because the resonances apply torque proportional to the square of the mass of the planet, the impact time would go like 1 over the mass of the planet, and you wouldn't be able to get any larger bodies. This doesn't just mean no Jupiters, it means no, I don't know the exact cutoffs, it depends on disk parameters, but this is one reason why it's thought that planets, like Earth-like planets, don't form during the gas phase of the disk because they don't have enough gravity to overwhelm the disk and push it away from the planet, but so they get pushed along by the disk and actually just go into the star. But if you have Newton's third law, you get a big enough planet together, then it can actually overwhelm the disk and just push the material away instead of being pushed along by the disk, and it carves out a gap in the disk. I'll show that here. So here I plotted in log radius versus log surface density the outermost 5 resonances, and I'm only including resonances here that have strengths of order eccentricity, or basically for circular orbits, so to 0th order in eccentricity. So these are 1 to 2, 2 to 3, 3 to 4, up to 5 resonances here, and remember there are a lot more resonances inside here. But basically what happens is out here the resonances are weaker, if you remember from the previous plot. These resonances further out are far from the planet, so they're weaker. But they're also less dense out there, so they don't affect disk structure very much, but the planet really clears out a gap close to it due to just its torque exerted on the disk. Then disk viscosity makes disks spread out and fill in material in the outer resonances here. So the material entering the gap interacts with those resonances, and this is what drives so-called type 2 migration. So video here showing that. So it might look like the planet is slow. Looks like it's. I don't know. It looks like it's lagging. Well, anyway. Yeah. So, alright. So the planet will migrate along. I wonder if it'll keep going. No, that's all we get. Okay. I don't know what happened there. Alright. So anyway, the migration videos might not work, but you get the idea. The outer resonances get a little extra material from the disk spreading out. So it's type 2 migration. But when the disk density isn't quite as smooth, You can get other factors that affect where planets can be stopped. So some other ones are called the dead zone, where the disk density is so thick that it's less ionized. Less ionized means less viscous and less, and basically more dense. So, so if you imagine a planet coming in from the outside here, those blue break resonances can interact with the denser part of the disk and have a bigger impact and stop the planet. Also the ice line heat transition, but I don't want to get into the details there too much. All right, so this is the model I'm working with. So a canonical sort of model of photoevaporation is that there's this location called the gravitational radius, which is the turnover point between really hot, so these are like over 10,000 Kelvin disk material being bound by gravity to the star and not being bound. So the idea is the photoevaporative flow is launched when you can exceed the gravity of the star with just the disk temperature, and then that the flow amount sort of decreases as you go out just due to the decrease in flux of the ionizing radiation. All right, so I added this photoevaporation model to a planet migration simulator called Fargo, and this is log surface density versus log radius over time. Let's see how far along this video goes. Okay, so you can see the photoevaporation on simulation starting to diverge from photoevaporation off simulation. And let's see maybe if I can skip to, yeah, there we go. Okay, so if I sort of skip along here, you can see the part of the video that wasn't showing where eventually, on order of 5 to 10 million years, photoevaporation will create a gap in the disk. So the simulation I ran. Then, so these are some calculations I did using some previous work by James Owen, so thank you for that work, on X-ray photoevaporation of disks, where I inserted artificial planet gaps into the disk, which, oops, they're not that artificial, there we go, because they're based on planet migration simulations. They're the same size as they would be for a regular disk. So I inserted those into the disk and then calculated the torques on the planet due to the disk at different locations, so if the planet was just sort of dropped in there with its gap, and showed that the migration time field kind of skyrockets as you enter these gaps, so that that's the planet's planet trap sort of working there. And then I made a little video here. I'll just start it this way. So this is late in the lifetime of the disk. This is the exact same photoevaporation video I showed you before, except I put in dropped a planet gap into it. And put some resonance design. Remember, these are green for go resonances, blue for breaks resonances. And planet will still migrate along, though slower than the case when the disk has a higher surface density, because it's really depleted now. But eventually what happens is the interactions between the outermost resonances and the disk. Let's see, show this. So eventually the disk can get drained behind the planet, and basically the go resonances no longer have material to push the planet along, but these breaks resonances still have their torques acting on the planet. So this planet will find an equilibrium between these where it'll stop the planet from migrating. So that might look a little fine-tuned too, but you can imagine if the planet was actually, so go to here, if the planet actually started out outside the gap to the right of the gap there, then the breaks resonances would be weaker. It'd actually be accelerated until it got to this equilibrium point where the torques balance out, and the planet stops. Also, I should note that some previous work has shown that the planet can also stop just outside the resonance gap, where I just told you it would be accelerated if basically depending on your model of planet accretion. So whether or not the planet allows material to travel through its own gap in the disk. And then just some comments on some previous work. I didn't include a slide for Alexander et al. 2013, but I probably should have, because he basically did the same kind of thing that Ercolano and Rizzotti did here in 2015 in April. And these are some differences between our papers here. And yeah, so that, I'll take questions. Yeah, in the back.
So if photoevaporation causes the disk right before the planet, then we will create a type 2 migration much enhanced to the star, right?
Yeah, depending on the planet's accretion mechanism. If the planet is accreting gas material, then it can actually stop a lot earlier, because it'll sort of contribute to that gap formation and basically just make the gap widen a lot faster, because it's not letting material refill the gap. So it can actually artificially end planet migration a lot earlier. But yeah, if the planet is not accreting very much, it's just kind of migrating along with zero accretion, then yeah, that's yeah.
So that could explain this one EU bump, right? Either photoevaporation cuts you after the planet just migrated and it stops there, or if photoevaporation breaks the disk right before the planet and you get rid of it into the star.
Yeah. I mean, I think you can definitely if you don't include planet accretion, then you can make that happen.
So two sort of related questions. One is whether these gaps that you get just from photoevaporation could possibly explain gaps that have been seen in all the disks that have so far been looking into gap pattern planets.
Yeah.
And then the other one would look like in your, so you have in the model where you have photoevaporation plus planet, you have this sort of double gap. You seem to recall seeing some images recently of these almond disks.
Okay. Yeah, I should have. Okay, so first I'll talk about the first question. Let's see. Sorry, what was the first question?
So that was just the photoevaporation model.
Oh yeah. So one important factor is that the disk density is depleted a couple orders of magnitude over the let's see, it goes from between 4 and 5 there, the inner radius, to between 5 and 6. So maybe an order of magnitude and a half by the time the photoevaporation gap starts to open. So these disks, I'm not sure is the short answer. I would think that they're so depleted that you might not see much of a disk anyway. The gap. So I don't actually know. I mean, there's some difficulty there, and this once this gap starts to open, the disk doesn't last much longer. So there's also a detection bias against finding this transition part of the disk, because this doesn't last very long, but it does last a comparable time to the planet migration time scale around that time. So that, and then this double peak is very artificial. Sorry, I should have mentioned that. I just sort of dropped the planet gap in here, but realistically, this bump here would never exist. The material coming into this gap would be photoevaporated and never sort of refill this region. So that's just one way of the video. Yeah, James.
So I can comment on the previous two questions. That on whether the planet will get thrown in, the disk is too depleted by the time photoevaporation opens the gap for that to matter in this case. And are the almond gaps created by photoevaporation? No. We clearly know that now. So something else is causing it.
Okay, yeah, thank you.
And my question is, have you compared your 2D torque migration rates from farther with the impulse approximation that everyone else is using?
You mean the Pringle diffusion, or the?
So the formula that Alexander and Vespucci and Rossotti and Etelano use.
I have not. No.
That would be an interesting thing.
Yeah, and certainly once I get planets into the working in the photoevaporated simulation, I can compare. I guess one thing I'm kind of concerned about is just how rigorous those are with variable density distributions in the disk. So just comparing those, those situations. But yeah, I'll definitely.